Hi, welcome back to Moose in Chemistry. This lesson is Electron Configuration Using Quantum Numbers, Lesson 1. This is based upon basically the Pauli exclusionary principle, which states that no two electrons in the same atom have the same set of 4 quantum numbers. Okay, so what does that mean in plain English? That the quantum set numbers for hydrogen, the element hydrogen, are not the same quantum set numbers for the element, say, carbon. That each element has its own unique set of quantum numbers. So what are the 4 quantum numbers? Well, let's look at this. So, for example, let's look at the first one, which is called the principal quantum number. So we're going to write that down. And that is denoted by the letter N. The second thing we're going to look at is the angular momentum quantum number. So I'm going to go ahead and write these all out first, and then we're going to actually get into doing this. And it's really not that hard. It's really amazingly easy. And that is denoted by the letter L. Okay, then comes the magnetic quantum number. That'll be the fourth one. Third one, actually. As that's denoted by the letter M. And then last is the spin quantum number. And that's denoted, let's get that. That looks horrible. There you go. It is denoted by S. Now, the principal quantum number deals with period levels, like 1, 2, 3, 4, 5, 6, and 7. The angular momentum number, okay, that deals with the shape of the orbitals. And is there a lot easier way to talk about that? Yes, there is, and we're going to get into that. The magnetic number symbolizes the orientation of the electrons around the nucleus. And then the spin number indicates whether the electron is spinning clockwise or spinning counterclockwise in order for it to stay in the same area. Because remember that electrons are the same charges, and they absolutely despise each other. They don't want to be around each other. So let me go ahead and clear all these drawings, and we're going to kind of make a table here, which will make it a whole lot easier for us to see. Okay. So now, let's start off with the principal quantum number. That's N. So it's going to be 1, 2, 3, 4, 5, 6, and 7. The next one is the angular momentum number. Okay. Now, the angular momentum number deals with, like, for example, if you're an S block element, your value is 0. If you're a P block element, your value is 1, D block 2, F block 3. Okay, the magnetic number is talking about how where its orientation on the axis, and we'll get a little bit more of that in just a few minutes. The M number, if it's an S, has a value of 0. If it's a P, it is equal to -1, 0, 1. These are the possibilities. D is -2, -1, 0, 1, 2. And then F, of course, is going to be -3, -2, -1, 0, 1, 2, 3. And then last but not least, the fourth quantum number, which is our S value, is going to be 1/2 positive, and that's going to be an up arrow. Remember Hund's rule? or it's going to be 1/2 negative. Down rule. So what does this mean? This means going clockwise, and this means going counterclockwise. Okay, so that's the table. So again, let's kind of look at a very primitive drawing of the periodic table here. Let me go ahead and sketch it real quickly. All right, there's our sketch of the periodic table. Now it's broken down into, like, where's the L values at? Okay, we know that the N values are 1, 2, 3, 4, all the way to 7. Okay, we understand that. Okay, that's our principal quantum number. Our angular momentum quantum number represents what the shape of the orbitals are. And so, for example, this would be the S block. So anything in group 1 and 2 are S blocks. This is called the D block. With the D block, you have something called N-1. That's the principal number minus 1. So that tells us why, when you're looking at the fourth row going across, you'll see that there are actually 3 Ds in that row when you look at the diagonal rule, and that explains that. And then, of course, the P block is over here, and that is groups 13 through 18, with the exception of helium here. Helium is actually in, well, technically it's 18, but it's technically an S block, so helium's S block, hydrogen's S block also. Okay? And then, and this is 13 through 18, and this guy would be 3 through 12. And then, those are the group numbers. And then, of course, down here is the F block, which is N-2. Okay, so let's pick an element from the periodic table. Let's pick, we said hydrogen earlier today. So we want to know, what are the 4 quantum numbers of hydrogen? All right, so we have hydrogen here. Hydrogen is in the, okay, so we go N, L, M, and S. Hydrogen is in our first block, or first row. So it's row 1, so it is energy level 1. It's in the S block, so the L value under L is 0. It's in the S block again for the M, so that's 0. And hydrogen is the first element in that block. And then, of course, the next one beside it would be helium, technically. And that would be, helium would have a down arrow, but hydrogen would have an up arrow. So it would be 1/2 positive with an up arrow. So that's the unique set of hydrogen. Let's look at helium. Okay, helium is also S block. So it's in the N value of 1. It's in the first period. The L value is 0. The M value is also 0, looking at the chart above. And the S value is going to be 1/2. This time it's going to be negative. It's going to be a down arrow. And you can see, according to Pauli exclusionary principle, again, which states no 2 electrons in the same atom have the same set of 4 quantum numbers. Okay, this number is the same. This number is the same. This number is the same. But this number is different. Okay? So they don't have the same set of quantum numbers. So let's look at another problem. And like I said, there will be further lessons on this. This is just basically an introduction to how to do quantum notation. And quantum notation is just one way of us being able to tell, hey, if I knew the 4 quantum numbers of an unknown element, could I determine what the identity of that element is? And the answer is obviously yes. Okay, let's look at 2 more. Let's take scandium. Okay, now scandium, if we look at a periodic table, remember we have N, L, M, and S. Now scandium, it looks like it's in the 4th row going across, but remember that scandium is in the D block, which is N-1. So you would go For the N value, you would say 4 minus 1, which gives us an N value of 3. The L value is going to be 2. The M value, in this case, is going to be negative 2. Why? Because scandium is the first element going across the periodic table. And we need to show you in another lesson how that works. All right. Now, it's going to have an up value with the S, so it's going to be 1/2 positive. Okay. So let's look at the next one, which is titanium, Ti. Ti is also has an N, L, M, and S. And so titanium again is in what appears to be the fourth row, but it's in the D block, so it's 4 minus 1. So we get 3. The L value, of course, is 2, like the one above in scandium. The M value is going to be negative 1, because we moved one element over on the periodic table. The S value is going to be 1/2 positive. And this does satisfy Pauli's exclusionary principle because, look, our M values are different. Okay, well, I hope you enjoyed this introductory lesson into Musin chemistry with quantum numbers. You guys have an awesome day, and we look forward to seeing you again.